Okay, so the topic here is a continuation of last time, where we have a few more good problems left in the bank of combining fractions, percents, and ratios. And then, time permitting, we'll jump into some stuff involving connecting punctuation and take it from there. So here's the first one. Go ahead and when the problem shows up on the board, go ahead and give it a shot. This one right here. Okay, here's a timer for you. Remember where the multiple choice responses are. There they are. Please use those options. Please do not post your, I mean, the other people in the room will not see your answers. So please don't post them in the chat box. All right, here's a clock. Give it a shot. Okay, so sorry for the brief delay there. Time is expired. Here are your class responses to this problem. By the way, it's data sufficiency, and we do expect a certain amount of familiarity with how data sufficiency works. So if any of you guys are total newcomers to this stuff, then you're going to want to at least familiarize yourself with the basics of how these problems work. But we assume that you guys in the audience know what sufficient and not sufficient and what the answer choices mean on these problems. So here are your class responses right there. There's a lot of non-responses here, so this is not great. I mean, remember that when you have non-responses, you're not really simulating the actual test that you're going to take. So, I mean, one of those is me, but that means there's 12 people here who gave me a non-response. So, I mean, again, not to sound like a scolding elementary school teacher, but please don't do this. Like, don't not answer the question. Because the GMAT makes you answer everything. Like when you take this test, you cannot leave the problem that you're on and move on to another one until you come up with something that is a thing. So, okay, but we are sort of all over the place on this one. Before we get started on looking at ways to solve this, let's also remind you of a theme that will carry over from previous lectures, which is what's the point of going over problems like this? Like, what's the main goal of reviewing math problems on this test? I mean, tell me in the chat box, what are we trying to do primarily above all else when we review math problems? The goal is what? So determine what's needed to have sufficient. I guess I'm looking for something more kind of abstract than that, or like what is the point of? I mean, you do have to understand sufficient and not sufficient. That's true. But I'm talking about like what is your goal when you go back and review any math problem at all on this test? I mean, you're primarily trying to find what. Okay, getting warmer with that one. Learn concepts to apply to other problems. Yeah, because I mean that's one thing that's good. You want takeaways that are actually going to apply to other types of things. Because remember that you're never going to see a problem that is an exact copy of another problem. So this is a good point. I mean, you need generalizable lessons. If you have something that's too specific to the problem at hand, then even if it's brilliant, then being too specific is still kind of an issue. So let's see what else. See where we're going wrong. Takeaways is the same sort of thing. Someone said this. What do you guys think of that? Are there any thoughts on that chat box? Is it about trying to figure out the fastest approach? Is that what we're trying to do? John says no. Yeah, it's not. I mean, we're not trying to figure out what approaches are faster. That's not really the point. And someone else is saying best approach. That's not really a good way to think about this either. Because why not? Well, the problem with these two things is that they're not things. I mean, remember that if something is the fastest approach on one problem, that tells you absolutely nothing about what will happen on any other problem later on. I mean, the fastest approach on one problem might be unworkable on another problem, or might be really slow if it does work. Same thing with whatever is the best approach. I mean, if there is, I mean, first of all, there's not really such a thing as the best approach in the first place. Because, you know, if something solves the problem, then it's just as good as something else. Like, there's no such thing as solving the problem better than something else. I mean, it either does or it doesn't. So first of all, this is not really a thing that even exists. But secondly, it doesn't generalize from problem to problem. So it's basically an extension of what we set up here. I mean, these things are totally not generalizable, so you just shouldn't worry about them. I mean, there's no, these are only things on single problems. So the point is not that. The point is to just come up with as many ways to solve these things as you can. So, and we've said this in other sessions too, but make sure that when you are going back and studying these problems, that you do have this in mind as a goal. So the main point of review is to come up with, find as many ways as you can to solve the problems. And another thing about this idea is that you should, what do you guys think? I mean, let's see in the chat box. Do you guys think you should focus on methods that you are most comfortable with, or do you think you should focus on methods that you are less comfortable with? What do you think in the chat box? Yeah, it's the ones that you're less comfortable with. Because one thing you'll learn about this test is that this is not, I mean, this is a test where you're not going to be learning a lot of new stuff. I mean, the math that's actually tested here is definitely not advanced or obscure. So it's really all about strategy, and if you're just applying strategies that you already are comfortable with, then it's not really gonna help. So you should find as many ways as you can, but you should, in particular, you should concentrate on methods that you don't like as much, that you're less comfortable with. Because that's the point. I mean, you're actually building a skill set. So for example, if you really like using algebra a lot all the time, then if there are non-algebra ways to solve the problems, then that should really be what you're hammering when you review these things. Because you're trying to build a better and more diverse skill set. So just make sure you keep these things in mind. Because what a lot of people do when they review problems is they just kind of go over the problem in exactly the same way they did it the first time, which is not really going to help anybody. I mean, if you're just reinforcing things that you're already good at, then So, okay, let's take a look at this problem. Let's take it over to the next slide. Okay. Who's got an approach to this? And I will tell you there's going to be some learning happening here because there are not a whole lot of correct answers to this problem. In fact, I will go ahead and give away the game and tell you that The correct answer is the single answer that people pick least often. The answer to this problem is actually A. So, a lot of learning going on. Let's take a look. Well, who's got an approach to this thing? Anything. Let's just throw out a possible way of starting the problem. So, I mean, and first of all, before we even start the problem, make sure that it's one of our posters said this earlier, the first thing that you should do on all of these, the first thing on any data sufficiency problem is to make sure you understand what sufficient and not sufficient specifically mean in the problem at hand. So in this case, this is not a yes/no type of thing. This is a question where we want a number. But it's more than just value or yes/no. I mean, that's the first kind of step here. But you want specifics. You want things that are actually actionable. So if it is a yes/no, you don't want to stay in terms of yeses and nos. If it's a value question, you don't want to just say, oh, it's a value question. You want to actually say, what am I trying to find? So like here, sufficient means that only one remainder is possible. I mean, make sure you get that in your head at least. You may even want to write it down just so that it's a focus for your attention. Not sufficient means you can get two or more different remainders. So, I mean, this should be routine. I mean, this should seem like no big deal. But if you guys aren't figuring this out before you start, then the problem is there's no goal for the rest of everything. So, okay, let's talk about testing cases. Okay, well, because one thing you can do as a primary method on data sufficiency is you can, Praveen says you can pick numbers. Let's try that. So for statement 1, let's find cases of positive integers A and B for which that statement is actually true, for which B is 60% greater than A. Okay, well, let's find some of those. Well, 60%, right? So Abhishek, yeah, I mean, one thing you're going to realize, even if you have no idea how to do this as an algebra thing, one thing you're going to realize pretty quickly if you start looking for cases is that your numbers are going to have to be multiples of 5. Because, I mean, making the fraction connection here will help you. So that's one thing you can do for additional insights in general, is if the percentages are not really helping you, then get them out of percentage form and see if they help you in other forms. So this is the same as 3/5. So yeah, you need, like, it's that much greater than A, which means that you have to have an A that you can take 3/5 of. So, and I mean, if you don't realize that, if you just trial and error, if you just throw a bunch of numbers in there and try to do this, then it'll be pretty clear after not too long. So, okay, so in other words, if A is the smallest possible number you can do this with, would be if A is 5. So then B would be 60% more than 5, which is 60% of 5 is 3. So that's 8. And then AB is 40. So the remainder when you divide 40 by 40 is 0. All right, well, let's look at a couple more cases, right? So you've got A could be 10. So let's look at that case. If A is 10, then 60% of 10 is 6. So 10 plus 6 is 16. Looks like AB is 160. And then a remainder of 160 divided by 40 is still 0. I mean, I think you guys see where this is going, but you want to look for a pattern here. What you're going to eventually recognize is that your A is always going to be submultiple of 5. So, I mean, throw in enough cases until you kind of see what's going on, right? A is submultiple of 5. And so because you're increasing that by the same 60%, B is going to be submultiple of 8, which is 60% more than 5. And just look at enough cases to notice. You get 8, you get 16. If you do 15, you'll get 24, and so on. Yeah, so that means that AB is submultiple of 40, which means that your remainder is always going to be 0. So this statement's sufficient. There's a couple other ways that you can deal with this. You can translate the percentage. Lynn points out that you can translate the percentage into fractions entirely. So let's put that on the board here too. In fact, we'll take that over to the next page. But yeah, B is 60% more than A, which means B is A plus 60% of A. In terms of fractions, that's A plus 3/5 A. The point being, make sure you're okay with converting these fractions. So B is 8/5 A. That's a useful observation if you're going to take an algebra type of approach or theory to this, which we'll look at in a sec. Jen says, why does A have to be a multiple of 5? Well, because you have to, I mean, again, see, this is why testing cases is your friend. I mean, in terms of questions like this one, because if you don't test cases, then this question that Jen is asking here, if you don't test specific numbers, then you have this problem where you have to like immediately understand exactly why everything is a thing. Whereas if you do test cases, then all you have to do is just try numbers, and then you can kind of notice as you go along that, okay, these kinds of numbers work and these kinds of numbers don't. Like if you, I mean, Jen, if you don't see why you have to have multiple of 5 here, just start taking some numbers and seeing whether you can even do this. Like seeing whether you can have 60% greater than those numbers. I mean, you'll discover that you have to have a number that you can take 60% of and still get another integer. So, like 60% of 1, 2, 3, and 4 are not whole numbers, but 60% of 5 is. Then 60% of 6, 7, 8, 9, that doesn't work, but 60% of 10 totally does. And eventually the pattern will just throw itself at you. So that statement's sufficient. We will look at Lynn's method in a second in a little bit more detail, but let's take a look at statement 2. So we need to find different answers to the prompt question. Again, when you deal with this stuff, it cannot be overemphasized how important it is to understand what the heck you're even trying to do in the first place. So let's look at statement 2, and let's see what's going on here. So let's test cases. Well, okay. So remember what the goal is. The goal is, can we get 2 different remainders when AB is divided by 40? So if so, then that's not sufficient. And if not, that's sufficient. Again, this is the most fundamental aspect here, but make sure that this is in your head before you get started. So, okay, you need to make this a thing. So one case here that's probably kind of obvious is that you can just let A and B both be 40, because then in that case you can definitely those are going to be divisible by 40. So one possible case is just let A be 40 and then let B be 40. So then that satisfies this for sure. And in this case, the remainder of AB divided by 40 is just going to be 0. Because AB is a bunch of 40s, so it's definitely multiple of 40. So now the goal here is to try to get what? What are we trying to find now? Yeah, we need to get a remainder that is not 0. So make sure you are all about this, right? The point now is find a remainder that's not 0 if possible. Well, okay. Well, if we think about this, we need the squares to be divisible by 40, at least one of the squares times the other number. So if I have something like, I mean, you may have to play around with numbers for a little while trying to get this to work, but if A and B are both 10, then both of those numbers are 1,000. So that works, right? 1,000 is divisible by 40. So that does satisfy the statement. But then the remainder of AB divided by 40, well, the remainder of AB divided by 40, AB is 100 in this case, so that's not 0. Remainder is 20, but the real point is that the remainder is not 0. So we got a remainder of 0, and we got a remainder of not 0. I mean, it might take you a little bit of poking around to find numbers like 10 and 10, but if you have a goal in mind and you realize, what you're trying to do is find this, then you'll have time to poke around with a bunch of numbers and see what happens. If you're just throwing random numbers in there, then you might not have time. Because once this happens, there's no point in trying numbers like 8 and 5, because 8 times 5 will just give you another 0 as your remainder. So you can just, okay, I don't even have to try those. And so you want to go for numbers that won't do that. Still not, not super obvious, but it's much more doable if you have that goal in mind at all times. That's in the green box up there. So we got 2 things to happen. It's not sufficient. So there you go. Let's take a look at this from a little bit more of a theory standpoint. So here you go. Lynn points out that you can convert this statement. This is statement 1 again now. Lynn points out that you can go to fractions, and 60% more than A is. Make sure that you guys can do these things, by the way. Like, make sure that all of the steps that are shown here are things that you can do without too much hassle. So B has to be 8/5 of A, which, if you think about what that means, what does that mean? I mean, in this case, the fact that they are integers definitely matters a lot, because you can think about their prime factorizations. Like, these are, if they were not integers, that would not matter. But these are integers, which means you can think about what primes they must contain. It's a connection you might just want to make, even if it's not like, even if nothing says primes in the problem. When you think about divisibility, divisibility has to do with primes a lot. So, if you're stuck on thinking about other stuff, there's a connection that is a thing a lot of the time. So let's think about that. Well, the point is that 8/5 A has to be an integer. So notice what this expression does. I mean, this expression basically divides A by 5. So if that still winds up being an integer, then that means that A has to have a 5 in its prime factorization. So if this is still a whole number after dividing by 5, then A must have contained a 5 in the first place. So we know that, and then notice what happens with B. B is the result of dividing A by 5 and then multiplying by 8, which is a totally different prime. Like 8 is 2 to the third. There's no 5s in there. So what this means is B is 8 times something that is an integer, which means that it has to have an 8 in it. So you can observe that B contains 8, which if you're thinking in terms strictly of primes, that's 2 times 2 times 2. So that's enough to realize that you've got a multiple of 40 going on here, because A has a 5 in it, and B has an 8 in it, so, or 3 2s if you want to think about primes. So A contains a 5. B contains 2 times 2 times 2. So that means that AB contains 5 times 2 times 2 times 2, which is 40. So your remainder is 0. And I mean, again, if you don't, the point is let's get as many ways as we can to do this. Like if this is not a thing that you would think to do, then there's two things. The first is you should review it and see if you can build that kind of intuition, especially the intuition that lets you think about this in the first place. So, but more importantly, if you don't think to do something like this, no big deal. Just do that instead. Just start plugging numbers. So either way you win. I mean, there's nothing less appetizing about a number plugging solution than about a not number plugging solution. So, any questions about that? If you look at statement 2, we can also do that in terms of theory, although as you're going to find out, the theory for statement 2 is not the easiest thing in the world. But again, that's the point. Testing cases is a thing. So, but we'll look at it real quick without, again, the theme is fractions, decimals, percent, so not to get too far off track with this. But so what this means is, let's think about this in terms of primes, statement 2. So I'll walk you through basically what the reasoning is here. So A squared B, which means A times B, is divisible by 2 times 2 times 2 times 5. So what has to be a thing? Well, the first thing is you have to get a 5 from somewhere. So that means that either A or B has to have a 5 in it, because you got to get that 5 from somewhere. So either A or B has a 5 in it. It's prime factorization. Now, this is where it takes a little bit more thought, and this is why you might just want to jump to testing cases if this is kind of over your head. But if not, dive in and at least make an effort, especially when you review, to understand this. Okay, well, we need to get 3 2s out of this. So let's think about where those would come from. Well, you got 2 A's in there. So if A contains a pair of 2s, then that will cover this all by itself. Because if A has 2 2s in it, then you'll have 4 2s when you multiply the A's together. So one way you might have that happen is A contains 2 2s. Or if all the 2s are coming from B, then B is only there once. So if you get all of this out of B, then that means B has to have all 3 of those in it. So Another case is B contains 3 2s. Or you might get contributions from each thing. So if B has a 2 in it and A has a 2 in it, then you will get 2 times 2 times 2, and so you can also get it that way. So both, the other case is that both A and B contain 2s. Okay, well, and then you can do the same sort of thing with the other case. You also know that A times B is divisible by 2 times 2 times 2 times 5. So the reasoning here is kind of the same. We still know that either A or B has a 5 in it. So, and then we just switch the roles of A and B here now because now B is the one that appears more than once. So we just take the same statements that we had up there and just change where it says A and where it says B. And then we know that all of these things have to be true. So this might be a little bit overwhelming. And if it is overwhelming, the most important thing to say at this point is, whoa, just start testing cases. Like, if you get lost in this reasoning, then don't keep doing it under time conditions. Just switch to testing cases. That's the most important thing you can take away strategically here, is don't struggle under the time condition. I mean, you can do all the struggling you want when you review the problems, because that's the point. The point of reviewing the problems is to try to get all this to click. But when you're under a time condition, the last thing you want to do is sit there and struggle with the problem. Like, you want to just get the heck out of there. It doesn't make sense. So, okay. But one way of making this work is you can think about specific cases. But if all of this is true, then the only thing we really know is that these things are true. So we know there's a 5 in there, and we know that one of these things is true. But that can still give us more than one remainder. Like, we can get a 0 remainder. I mean, this should be pretty clear. Just make lots and lots of 2s and 5s, and you can make that. But then if you have a case where if you have this case, that's where we get, a 10, but 10 and 10 can come from there, right? Like, it also works if either you just take one of those cases and look at it. If either A or B contains a 5, and each of A and B contains 1, 2. So, for example, 10 and 10. Then that gives a non-zero remainder. Again, this may be horrible, but the point is that it's not the only way to do it. If you get stuck on that reasoning, then you can just do this instead, and you can just try to come up with numbers that will do that. So, and don't forget that your main goal here is to just find as many ways as you can of doing the problem. And in particular, if you're not down with the whole testing cases thing, it's the new trend. You definitely want to get on that. All right, so there's a lot of questions in the box. Let's see. For some reason, the chat box doesn't update. Okay. All right. Questions in the box. Someone asks this. So anytime a fraction and integer is an integer, as long as the fraction is reduced, yeah, because reduced meaning you don't leave like 3/6 as 3/6, like you would make that a half. So I mean, just look at the example of what we had there. of 8, 5b. And I mean, you can, this is going to, there's nothing special about 8 and 5 here. Like the point is that you have to be able to divide b by 5. And then once you have that, you multiply by 8 to get a. So yeah, you're always going to have this kind of connection. You're always going to have that and that. Those are always going to be things. So okay, and then let's talk about this. I mean, I don't love the words prove and disprove here because data sufficiency is not about disproving anything. But this is a useful thing to think about. Like when you do theory type approaches, like this approach here where you're, where are we at? Like when you're trying to do this, your theory and algebra and so on are generally aimed at proving that things are sufficient. So when you do theory or algebra or textbook stuff, you usually try to prove that things are sufficient because that's what algebra does when it does stuff. It's like, oh, I got the expression that I wanted, and so sufficient, or I got a value out of the algebra. But when you test cases, though, it's not that. Because remember, you can't really prove sufficiency by testing cases. I mean, you can see a pattern, and you can be like, okay, I see a pattern, and blah, blah, blah. But the real advantage of testing cases is that you can actually come up with two different things, and then they are two different things. So, like, when you test cases, that's the only thing you can really do. So, like, when you're doing this, okay, I got a 0 remainder. I mean, the point is that further cases of a 0 remainder will not help me. So when I'm testing cases here, I just try to find other remainders. Here, I don't get any, which means it's sufficient. But when I'm doing this thing, okay, I got a 0 remainder. If I get additional 0 remainders, it doesn't help me. But the goal is to find the other possibility. And that's why these two methods are such good complements to each other, because they have different emphases. Like when you test cases, you always try to prove that things are not sufficient. Because that's what testing cases is. Like you're trying to be like, oh, can I get two different things to happen here? It's not what algebra is. Algebra is, can I get this to condense down into this cute little expression that I wanted? But testing cases is not, let me condense and simplify. Testing cases is, let me see if something will turn out more than one way. Okay, let's move on to another problem. So, as far as the screenshot, yeah, the recording will be there by Monday or something like that. So, just so that we can get some more stuff here in the time that we have. So, try this. Okay, remember where your answer choices are found. The other thing, too, is that this is a longer problem. So also remember that longer problem, in terms of words, like when there's more words in the problem, these are your A, B, C, D, E. I mean, the numbers that are there. I mean, so like that's A, that's B, that's C, that's D, and that's E. When you have a longer problem, what does that mean when a problem is longer, as far as just general point of strategy here? When there's more stuff in a problem, that means you can what? Anybody? Nobody? What does it mean when a problem has more words in it? Yeah, you can take longer. I mean, that's the point. So Ian is going after what I'm going after here. I mean, you can definitely take more time than average. So like limiting yourself to 2 minutes for a problem like this may not be the smartest decision in the world. I mean, in other words, just make sure that you're not thinking that 2 minutes is a time limit. Remember that 2 minutes is an average, not a boundary value. So, feel free to take more than 2 minutes on a problem like that. So here's a timer. Let's try that. Remember where the multiple choice options are. Go. Okay, so it looks like this is a time challenge because I think we've only got like 20 answers out of about 40 of you guys who are here. So take an extra 15 or 20 seconds if you have to. But again, remember that a big part of strategy on this test, if not the biggest part, is learning when to fold them and let it go. So if you don't get an answer to this in the next like 15 or 20 seconds, then just guess something. But take 15 or 20 seconds. All right, ladies and gentlemen, again, if you are still banging your head against this problem, then just pick an answer. And again, for some people, I mean, don't underestimate the value of the just pick an answer thing. I mean, for some people taking this exam, that's actually the single thing that's going to improve their score the most, is learning to just let go and pick stuff without killing yourselves. So, okay, here are the class responses. So there's still a lot of non-responders. It looks like some people are guessing some things too. So let's see. Again, if you are one of this crowd that's right here, the non-responder crowd, don't be. I mean, make sure you answer the problem. Okay. Let's talk about it. Let's say you wanted to do a solution that was algebra. So in this case, you probably want to start from the statement that m to n is 4 to 5. So let's talk about an algebraic approach. So ladies and gentlemen, how many variables do you actually need when you have a ratio that is like 4 to 5? You don't want 2. If you use 2 variables, it'll smack you as far as time goes. You definitely want 1 variable. So when you have quantities in a fixed ratio, use 1 variable. It doesn't even matter if they give you 2 variables. If they give you 2 variables, that means they're giving you too many variables, and you should get rid of one of them. So this is what our book, the strategy guide, calls this the unknown multiplier, which is kind of a mouthful, but the point is make sure you just know examples of it. I mean, like anything else, examples are your friend. So if you have 2 quantities in the ratio 4 to 5, like we have here, then you call them, like a couple people have said in the window, you call them 4x and 5x. This applies no matter how many quantities are in the ratio. Like if you have 5 quantities in the ratio, like 1 to 2 to 3 to 4 to 5, then that means you just call them x, 2x, 3x, 4x, and 5x. I mean, you can just do whatever. So in this case, we can get rid of m and n, and we can just let those be 4x and 5x. If you're doing an algebra approach, this is a key part of it. because you don't want to have to contend with a whole ton of variables. So ditch m and n. There's no point in having two variables here. Just call them 4x and 5x. Okay, so now make sure you know how to get from ratios to overall fractions. So here's the first part of the problem. In the first M games of the season, the ratio of the team's wins to its losses was 1 to 2. What does this mean? Like, this means that what fraction of those games were wins and what fraction were losses? In other words, make sure you can go, yeah, it's 1/3 and 2/3. Make sure you can go from ratios to fractions for each component. The point is that if you have a 1 to 2 ratio, that's like having a total of 3. I mean, it's a proportion. You don't literally have 1 and 2. But the fraction of wins here is 1 over 1 plus 2. It's your coefficient over the whole thing. It's not 50% because you know it can't be. I mean, look at this. You have more losses than wins, so it's definitely not 50% because you didn't win half the games. So you can check your result against that sort of intuition. 1 over 1 plus 2, so that's 1/3. And then the fraction of losses is going to be the other 2/3, which is 2 out of 1 plus 2. And I mean, this works no matter how many things are in your ratio. So I mean, if you had 5 quantities in this ratio, then 1 plus 2 plus 3 plus 4 plus 5 is what, 15? So this would be 1/15 of the whole thing. This would be 2/15 of it, 3/15, and so on. Yeah, you can write that, but what we're trying to do is we're trying to figure out how many total wins we had. I mean, Lynn, you're right about that, but we want, because these are totals. That's the problem, right? These are not numbers of losses or wins. These are the total number of games played. So in the first M games, which is the first 4x games, so that would be 1/3 of 4x. And so that's 4/3. I think I have this written up somewhere I can do it faster. Okay, yeah, you've got, this is 4/3 x number of wins. Let's downsize that real quick. And then similarly, you've got the number of losses that you have is 2/3 of 4x, which is 8/3 x number of losses. So there you go. And then in the next n games, which is in the next 5x number of games, so that is not n games anymore. This is the next 5n games, 5x games. You can do the same sort of thing. So you've got, you have 1/4 wins and 3/4 losses using the same kind of fractions that you had before. So these are your fractions of wins out of the total. Fraction of losses out of the total. So then you can do the same sort of algebra that you had before. You've got, that's 5/4 x wins and 15/4 x losses. Here's the work that gives you that. So, pardon the awkwardness of the eliminate. So 5/4 x wins and 15/4 x losses. And so now you're pretty much there. I mean, you have to contend with fractions. But in total, let's see what you got. Well, you can just add those fractions up. So let's move some of this up a little bit. Okay. So in total, we're looking at just adding those fractions together. So if you add up 4/3 x and 5/4 x, that's what you get. I mean, you got to just do that with the fractions. And then if you add up the losses, then you get that. So you can probably tell that we're looking at a ratio of 31 to 77. If you have to put these over each other and cancel things, then you should do that. But it's 31x over 12 and 77x over 12. So that's a ratio of 31 to 77. So that's an algebra approach. It's a thing. I mean, the other thing that you'll notice is you have to be organized. Like if you have scratch work all over the place everywhere on your paper, then the chances that you will be able to get through this without getting lost are pretty small. But if your work is organized, then it's not that bad. So, and I mean, yeah, Michelle said that was easy once you did it. I mean, there's no step of this that's not easy. That's the point. Like what makes this problem difficult is that you have to organize the work. And so those of you who are probably going to find this hardest are those of you who are used to just being able to, oh, look at a problem and know what it does. Because this problem, you cannot do that. Like no matter how math smart you are or whatever, there is no way that you can just look at this and be like, oh, dude, it's 31 to 77. Like you have to do the work and organize it. And so what you're going to find is that that's the problem. Like you definitely have to write stuff and make labels. I mean, I'm kind of doing it, taking it for granted, but writing things like this is a big thing. I mean, you need to label things. Definitely a big deal. So, because if you just have random fractions all over the page, and by the time you get down to the end of it, it's just, you're not going to remember what anything is. So you can also pick numbers. Let's talk about that. Snake, I don't know what you're asking me there. Like I don't know where you got those from. Okay. Let's see here. I mean, you can just pick numbers. So you know that you need M and N to be in a ratio of 4 to 5. So let's pick M, but we need to think very carefully about what kinds of numbers we need to pick here. We can't just rashly do this because there are lots of restrictions. So let's think about this kind of carefully. So the first thing is that we need to make this a 4 to 5 ratio. But then notice, and I mean, we're going to take for granted the fractions that we did on the other page because those are still things. So of the M games, you won 1/3 of those and you lost 2/3. So that means that M also has to be divisible by 3. Because you have to take 1/3 and 2/3 of that. And then let's think about the N games. So you won 1/4 of those and you lost 3/4 of those. So this needs to be, so 12 and 15, Ginny, that's getting there, but that's not going to really work because you also need this to be divisible by 4. So but let's use that as a starting point, and then let's just blow up the numbers until we get the other things to work. So Jenny, I don't really know exactly how to pronounce that, says, what if we pick 12 or 15? Well, let's just see what happens if we do. So that works here. The 4 to 5 works. The divisible by 3 works. But this doesn't work. 15 is not divisible by 4. So we just need to multiply this by 4, and then we're all good. So we can make this 48 and then 60. So once we have these numbers, this is the crux of the problem. Like once we have these numbers, it's actually very easy from this point onward. So like in the first 48 games, you have 1/3 of 48 is wins. So that's 16 wins. And you have 2/3 of 48, which is the other 32 games are losses. And if you have your subsequent 60 games, then 1/4 of 60 is 15 wins, and 3/4 of 60 is 45 losses. So your totals are 16 plus 15 is 31 wins, and 32 plus 45 is 77 losses. So there's your ratio, 31 to 77. But I mean, notice the thought that has to go into this. This question on the board right here, in this particular case, it's not going to accomplish much because they're not ratios in the same context. Like there's no reason to make these look like each other because this is a ratio of the first bunch of games. And then this is a ratio of a totally different number of games, like a totally different set of games. So like these ratios are not comparable to each other. So there's not really much point in doing that. But in a case where they would be, then it could possibly make sense. Again, notice the point. Make sure you can do this by algebra. Make sure you can do it by plugging in numbers. I mean, remember the point of reviewing this in the first place is if you like algebra, then concentrate on picking numbers. The point is to expand your horizon. Like if you like picking numbers, then concentrate on the algebra. It's pretty much whatever you are not loving, you should double down on. Is the idea. Okay, we should be able to do one more problem here, and then we are up against a harder schedule than usual as far as the end time. So, but we do have time for one more of these problems, which is Lynn, I don't know what the balance method means, so sorry. Okay, so here's this. Give this a shot. Play around with it. And here's a timer. Okay, pardon the delay there. So remember where your multiple choice answers are located. They are here. So make sure you pick something that is a thing. So let's take a look. And if you need to guess, go ahead and get a guess. Here are your class responses. So, all right, kind of all over the place again. Again, we have a certain number of non-responders, not to sound like a scolding school teacher again, but if you are a non-responder, you should not be a non-responder. Okay, so let's see here. Well, let's try to take an algebra approach to this. So if you want to do algebra here, you're not really going to get very far with this half of the statement, because that's half of a statement, and it's not a statement, so you can't really do that with algebra. But what you can do is you can take the statements and you can make them algebraic equations and just see if you can solve them. And if you solve them and get a positive integer, then you're good. So like for instance, in choice A, and this requires you again to make these connections between and among fractions, decimals, and percents. So if you do choice A, for instance, this is just an example. There's no good reason to start with any choice over another. It says that 1 over A is 25% less than A. As an equation, I mean, 25% less than A means 75% of A. So that means that it's a fraction. I mean, you want to make this a fraction because fractions are easier to solve. So put it to a fraction to make the algebra easier. So once you have that, then if you solve this, if you cross multiply, you get 3a squared is 4. So this is not going to be an integer. I mean, there's values that do that, but they're a square root weird values. So they're not integers. So, and the point is this is not slow. I mean, this is a very fast process. You definitely have the time to do this 4 or 5 times. If any of you guys are thinking, oh, I would not have the time to do this 4 or 5 times, yes, you would. You just have to try it. Like, make sure that you are not shy about trying these methods. Just throw methods at it. So, et cetera, keep working through the choices. So eventually you'll get to choice E. Choice E states that 1 over A is 75% less than A, which means that 1 over A is 25% of A. So once you get there, again, 75% less than is 25% of. Make sure you can make these connections too. Like make sure you know that this is the same as that. So you have 75% less than something is the same as 25% of the something. So that's also a thing that is a thing. So, okay. So if you solve that, then just a second here. Okay, if you solve that, you get this equation, if you convert it to a fraction. Cross multiply, you get a squared is 4. So this means that a could be 2. Could also be -2, but we want a positive integer. So a could be 2. So we're done, and that's E. Again, be able to convert fractions, decimals, percents, make sure you can work with a decent amount of agility between and among those different kinds of numbers. How else can you do this problem besides algebra? Anybody think of anything else? Yeah, just plug numbers, right? Because I mean, the thing that you should notice here is that A has to be a fairly small number. Because I mean, if you think about any numbers that are not small, they're not going to do this. I mean, like think about medium or like bigger numbers. Like I mean, think about say 10. You know, I mean, the reciprocal is 1/10, which is 0.1. I mean, this is 99% less than 10. I mean, this is only 1% of 10. So it's 99% less than 10. I mean, that's the point, is that with small enough numbers, it's going to work, but with big enough numbers, it just clearly won't. I mean, if you have even a number as big as 10, the reciprocal is so tiny that it's going to be a lot more or less than these things are. Like it's 99 versus these percentages. So we just need to try small numbers for A. So let's just try, it's not 1 because the reciprocal of 1 is still 1. So let's try small numbers for A, integers. Well, the first thing to do is to try A is 2. That's the smallest, not 1 positive integer. That means the reciprocal is 0.5. And that's 75% less than 2. If you, I mean, find that your standard way of finding those things. So 75% less than 2. Or you can just do it by inspection. I mean, if you have 2, then, 25% of 2 is 0.5. So therefore 75%, which is the difference here. The difference is 1.5, which is 75% of 2. Either way. So, but picking numbers here is your friend. And lastly, but not leastly, again, the point is to just absorb. I mean, you just want to be greedy. You want to just learn as many ways as you can to solve these. You're not terribly concerned with what's better or what's worse or any of those kind of false distinctions. Like, there's not really a better or a worse here. There's just things that work because they are things. So, okay, this makes a pretty logical stopping point. If you have any brief questions, then you can do that. Otherwise, we will, unless there are just fantastically fabulous submissions, we'll do the sentence correction stuff next time, the connecting punctuation. Because a few of you guys have been asking about, your colons and your semicolons and that kind of stuff. So we'll do that. That's probably going to be a topic next time, but again, it depends on what's submitted. So if you pick a different number, it won't work. I mean, the way the problem is written, only one of these can be a thing. So as soon as you find out that this one is, you're done. Because if another number worked, then you would have a problem with 2 answers. So it's not a thing. Okay, guys, let's go ahead and kill it. I'm going to turn off the recording.